Okay, so that's our example looking through with all the models. What we can then do is just have a look at how we're going to present this when we do written questions, when you don't have models. So feel free to play with your Play-Doh if you manage to find some, and to make as many models as you like today. So what we need now is a sheet that says how to calculate energy change for chemical reactions, and this is going to underpin your theory books as your examples. So it defines bond energy at the top, energy needed to break 1 mole of a particular covalent bond, and it gives you some hints when we're doing the calculations. So we need to always write out the balanced equation. We need to draw out all of the molecules showing all of the bonds. We need to work out how much energy is needed to break all the reactant bonds, and that always gives you your first exam mark, and work out how much energy is needed to break all the product bonds, which gives you your second exam mark. And the final mark comes from working out the total energy. So in that big banner there, you've got reactant bond energies minus product bond energies. So for our example, we are going to write a balanced equation for the reaction between ethene and bromine. So bit of a recap: ethene, one of our alkenes, eth, 2 carbons, so C2H4, bromine, Br2, and then bromoethane, it was an addition reaction, so everything just comes together like that. Okay, make sure that's in view for you properly. Now, we should remember this reaction. So this was how we test for alkenes. So bromine, water, can you remember what colour that was? Okay, so hopefully you've all thought orange. And then when it reacts with an alkene, it turns, and hopefully we've all thought colourless. So that was our test for an alkene. So that was part A. Filling in part B then, draw out all the molecules showing all the bonds. So we need to remember that our alkene has a carbon-carbon double bond, like that. Bromine has a single bond like that. And then in our products, our double bonds now opens up to allow the bromine to add in. So we've lost our double bond there, and we've got our 2 bromine atoms attached there and there. Now we need to work out the energy needed to break all those bonds in the reactants. Okay, so we have a look at what we've got. So we've got 4 CHs. So if I just put a little heading there to start with. So reactants is 4 times CH, carbon-carbon double bond. It's easy to miss those ones in the middle. Bromine-bromine bond. And we need to evaluate all of those. So we've got 4 times 4, 1, 2. Add 1 times 610 and 1 times 193, and if we add all of those up, 2451 kilojoules. We do exactly the same then for our products, so our bromoethane here. So we had in our products, remember those headings just for a bit of annotation, and if you've done something wrong, it's obvious to us where it went wrong rather than just strings of random numbers that we've got to try and decipher. Okay, so 4 carbon-hydrogen bonds, 1 carbon-carbon bond, and 2 carbon-bromine bonds. So that's 4 times 412, 1 times 348. So this is just taking the numbers from that table that you've got at the side of the sheet. And then that gives us 2556 kilojoules there. So our next stage is then to work out the overall energy change. So remember delta H, again, delta for change, H for the energy, just saves writing out energy change every time. We like our shorthand. So reactant bonds, 2451, minus product bonds, 2556, and that equals minus 105 kilojoules, and the units are always kilojoules per mole, if you can see that on the end, so moles to the -1. Let's just write in there reactant bonds minus product bonds, just as that reminder. Bonds. Okay, and have a think, is it exo or endo? So we've got our negative sign here again, so that tells us it's exothermic. Then the very last thing we're asked for in this particular question then is to draw a fully labelled energy level diagram. So we practiced doing that in the last lesson, as we mentioned earlier. So draw your axes out Let me straighten them up for you. So we've got energy and we've got progress of reaction. Oops, over there. So we need a line for our reactants. We know it's exothermic and energy's been given out. So our products are going to lie down here. If we know a reaction rather than doing just a generic one, then it's always good practice to actually split that equation balanced across your reactant and product lines like this. Then this difference here is our energy change. You can put delta H, you can label it energy change. And then sometimes questions like you to have the activation energy in. So if it's not needed, an examiner will just ignore it. But if it is needed, it's a good idea to just get used to always putting it on. So the activation energy is always the energy going from your reactant energies up to the top. Okay, so it's that initial amount of energy that's needed to break some bonds and allow particles to actually react. So we'll just label that one there. So that's activation energy. And that is how to calculate energy changes. Now, I'd like you to go ahead and have a look at the next question. And in that question, you are going to need to find out the energy change when we burn ethanoic acid. Now, just as a reminder, some of you might remember this from the acids topic, but ethanoic acid is CH3COOH. So it's an organic molecule, so it's counting in carbons, metheth, prop, bute. So eth for eth, ethanoic acid, 2 carbons here. We always draw it out like this rather than putting all the H's together and the O's together, because it shows us this bit here is what makes it a carboxylic acid, makes it part of the homologous series of carboxylic acids. So it's just a bit more visual. And then in drawing out the structure, we've got our first carbon bonded to 3 hydrogens, bonded to another carbon. Then this OOH bit, remembering that each carbon needs to form 4 bonds because it's got 4 outer shell electrons, so it needs a share of another 4. We can't just do the O's along here. We need 4 bonds around here. So we're going to have a double bonded O and a single bonded O before putting our final hydrogen on. Now this is going to burn in oxygen. So just have a think about what's going on. So we've got carbons burning in oxygen. What's the product? We've got hydrogens burning in oxygen. What's the product? And the oxygens, we're just providing a bit of extra oxygen there. So have a go through that calculation. The answer will be on the next slide in this PowerPoint. And then I would like you to practice doing these. So there are lots on the next sheet, on the question sheet, the one that's called Bond Energy Calculations. It starts off with them being very much scaffolded, giving you the A, B, C, D, E of draw out the equation and so on. Later on, it just asks you to calculate it. So you can refer back to those earlier questions for the scaffolding for all the stages. Or if you're happy with what you're doing at that point, then maybe you don't need to look back, but it's there if you need to. The extension ones are just pushing it a little bit harder, but it's all along the same theme. So have a go with those and see how you get on.